Since the derivative function is defined as a limit, it's possible for this limit to not exist. So if this limit doesn't exist for a particular x value, then the derivative doesn't exist for that particular x value. But there are several ways that a limit can fail to exist, and each way a limit can fail to exist actually looks different on a graph. So let's look at examples of all of the ways this limit could fail to exist and what that means for the graph of f, or what that looks like on the graph of x. So for one way this limit can fail to exist is just if the function isn't even defined at x, right? For this to make any sense at all, f of x has to be defined. So at any place where, so here's a graph of f of x, at any x value, say a here, where this function is not defined, its derivative also cannot be defined, just because f of x isn't defined. So if we went to sketch the derivative, right, these tangent slopes are positive and looks like they're getting smaller, so positive and getting smaller, but at this value a, there can't be a derivative here because this limit doesn't exist when x is a. So something like this. So if the function is undefined, what does that look like? There's just a hole in the graph, but that means that there will also be a hole in the graph of the derivative. Okay, another way this limit can fail to exist is if the two one-sided limits exist but are different. So remember, this limit is a two-sided limit. So if so this two-sided limit can fail to exist if the one-sided limits do exist but are different. So what would that look like? Well, here's an example of what that would look like. So you can see that from the left, the tangent slopes are all -1. And so if we sketch the derivative, it would look like this. From the right, the tangent slopes are all 1. And so the derivative to the right would look like this. But at 0, if you carefully work out the limit that gives you the derivative, it turns out that from the left it's -1 and from the right it's 0. And so the derivative is undefined at 0 just because the two one-sided limits are different. Well, you can see that what's happening here is there's sort of at this x value 0, there's sort of a tangent line from the left that's going down and a tangent line from the right that's going up. So really what's happening is it's almost as if there's two tangent lines, but since we insist that there be only one, we can't actually let either of these be the tangent line. And so we just have to say that the derivative doesn't exist at this point. So when this scenario happens, the two one-sided limits exist but are different, what that looks like on the graph is it's this sharp corner, right? It's the sharp corner that allows there to be a tangent line from the left and from the right, but for those two tangent lines to be different. So anytime you see a sharp corner, that will be a spot where the derivative doesn't exist. All right, another way that this limit that defines the derivative can fail to exist is if it's plus or minus infinity. So when I say exist, I guess I really mean be finite, exist and be finite. So what would it look like for the limit to be plus or minus infinity, or for the limit that gives us the derivative to be plus or minus infinity? Well, one way for that to happen is with this sort of graph, right? Now, but actually, this seems like an example, but it isn't really, because if we were asking about the derivative at 0, it's true that this function doesn't have a derivative at 0, but it's not because the limit that defines the derivative is plus infinity. It's because this function isn't defined at 0, right? So this actually isn't an example of this derivative limit being infinity. But so it's a little tricky to know what sort of picture would make a derivative try to be plus or minus infinity. But actually there's a pretty common function that is exactly what we're looking for. It's the cubed root function. Now the cubed root function looks like this. And you can see that the cubed root function is defined at 0, but what is the slope of the tangent line there? Well, the slope of the tangent line here is vertical, right? And so the slope of the tangent line isn't finite. Whether you want to call the slope of this line positive infinity or negative infinity is kind of up to you, but in either case, the slope of this tangent line isn't finite. So if we sketched a graph of the derivative of this cubed root function, well, the slopes of the tangent lines are small and positive, and then they get very big and positive, so like this, as x approaches 0. And then as we pass through 0, the slopes are large and positive, and then getting smaller and positive, so like this. So you can see at x equals 0, the cubed root function is defined, but the vertical tangent line means that the derivative is not defined at x equals 0. All right, one other way that the derivative can fail to exist is if the one-sided limits just plain don't exist. Right? The one-sided limits for the limit as h goes to 0 of f of x plus h minus f of x over h. Right, so what would it look like for these one-sided limits to not exist? Well, there are a few examples of that sort of thing happening. One is if we have a jump discontinuity like this. So for this jump discontinuity, the limit from the right actually does exist. It's whatever the slope of that line is. But the limit from the left, right, if you try to draw secant lines like this to get the slope of secant lines, and then you take the limit as this point moves towards the hole, these are going to infinity. So the one-sided limit from the left doesn't exist. Another example of this kind of situation is if we have one of these functions that wiggles around infinitely many times as x gets close to 0, it's possible that this limit will fail to exist. Well, later when we sort of have more tools for understanding the derivative, we'll revisit this example to see why exactly this sort of thing fails to have a derivative at 0. So an example of this sort of function is, say, x times sine of 1 over x. It just wiggles around too much to have a derivative at x equals 0. But this actually is a pretty delicate question, so this has no derivative at 0. This is a delicate question, though, because the function x squared times sine of 1 over x, it looks very similar. It gives a very similar impression. Right? This is essentially a sine curve, but whose amplitude goes like x squared. So that's like this, or like this. Right? So initially it looks very similar, but in fact this one does have a derivative. So this has derivative at 0. So this question of whether this, sometimes just from the graph it's not at all clear whether this limit that calculates the derivative actually exists. But to sort of zoom out and give you the big picture, the features of a graph that prevent a derivative from existing are a hole in the graph, right? That's going to prevent the derivative existing at that x value, a corner on the graph, a vertical tangent line, or, well, it's hard to give some sort of pithy summary of what is happening here, but it's wiggling around too much for the slope of the secant line to settle down on a value. All right, so we know what a derivative existing looks like on a graph, and if you look at all of these examples, for many of these examples, like this one here, or our first example here, really the reason why these graphs don't have a derivative at these certain x values is because, well, they aren't even continuous. It seems like to have a nice tangent line, at the very least your graph would have to be continuous. But it's not really obvious that that's true, so let's think about if that's true. So if a function is differentiable at a certain x value, let's call it a, does that tell us anything about the continuity of f at that x value? Well, we're kind of hoping that if it's differentiable, in other words, so when I say differentiable, what I mean is f prime of a exists. So we kind of think that if f prime of a exists, then that means that the function should be continuous at a. So the limit as x goes to a of f of x, we think that this should be f of a, right? Because this is what continuity means, right? This is the definition of continuity at a. But how could we prove this? I mean, we would have to have some calculation where we start with the limit as x goes to a of f of x on the left-hand side, and then some big calculation here, and at the end we have f of a. But it's hard to know how to fill in the gap here. So what could we do? I mean, we're hoping to fill in the gap because it just based on the graphs that we've looked at, it seems like if your function is differentiable, then it has to be continuous. Well, we have to get f of a to show up somehow, right? Because if we're hoping to end up with f of a at the end of our calculation, f of a had better show up somewhere. And there's really only two ways to get f of a to show up. One way is to multiply and divide by f of a, but I don't know that that seems like such a great idea. The other way is to add and subtract f of a. So we could subtract f of a and add f of a, like this, right? Because we're sort of intentionally unsimplifying what we started with, just so that f of a shows up, just so that we have some f of a to play with. Now this part right here, f of x minus f of a, that looks kind of suspicious because this is exactly the numerator of f prime of a. And we know that f prime of a does exist, right? We assumed at the very beginning that f prime, we assumed that f is differentiable at a. In other words, f prime of a exists. So it looks like the derivative is kind of trying to show up here. Well, let's make it show up. What's missing is the denominator of the derivative, which is x minus a, but we can make that denominator show up right here if we also multiply by x minus a. Right? Again, we've sort of intentionally unsimplified this fraction here, just so that this piece that looks like the derivative shows up. All right, well now we have this ratio times this piece here, and the product rule for limits says that this is the limit as x goes to a of f of x minus f of a over x minus a times the limit as x goes to a of x minus a. And then out at the end we have a plus f of a. Well, the product rule says that this is what we get, assuming that these individual limits exist and are finite. But remember, we assumed that f prime of a exists, and this first piece here, this is f prime of a. Right? We assumed that this is finite, exists and is finite, so that's just f prime of a. And what about the limit of x minus a as x goes to a? Well, that's clearly 0. So each of these individual limits does exist and is finite, so we are justified in using the product rule for limits right here. All right, and don't forget our f of a here. Well, look, now we have f prime of a times 0. That's just 0. So the only thing left is f of a. So remember what we started with. We started with the limit as x goes to a of f of x. And we did a big calculation, and we found that that's just f of a. So f is continuous at a. So, you know, the big picture here is that if your function is differentiable, it has to be continuous.